Hey guys, Ms. Peterson here, and today we're talking about the various components that make up our circuits in AP Physics 2. So we're going to be talking about how the battery supplies the electromotive force that drives the current around the circuit. We'll talk about resistors and how they're made, what properties determine their resistance, and ohmic versus non-ohmic resistors. We'll get into using Kirchoff's law to analyze a circuit and talk about how to use an ammeter and voltmeter to determine the current or voltage at any point in the circuit. If you're following along in the textbook, these are the sections. Again, this is from the AP Physics 2 curriculum, overview of these essential knowledge things, and there's a lot of really cool extension activities that go along with this lecture, some nice hands-on stuff that you guys can look into. Okay, so basically, whenever we're talking about a circuit, we are talking about charge flowing, and that flow is current. However, early scientists got current kind of wrong. They looked at current as flowing from positive to negative, the direction the positive charge would flow. We now know that it's actually electrons that flow in a circuit, but the convention stuck around. Okay, so current is defined as the amount of charge in coulombs passing a point in a given time. Our common units are amps, which are coulombs per second. You will also often see it written in equation form as the charge, which we know is Q, passing a point per given time. So charge per time, normally coulombs per second, is our current. Okay. Now, in the practical sense, whenever we're measuring anything about a lab, we're going to be using ammeters and voltmeters. Ammeters measure current, and they must be connected in series with a circuit, because we know that the current is the same across elements that are in series. Where voltmeters, which measure the potential difference, those must be connected in parallel with whatever you're measuring, because across two circuits, you're going to get the same potential difference when you're hooked up in parallel. And often, we're not going to have these circuits in front of us to manipulate and play around and find all of these things. But given just a couple pieces of information, we can normally solve out a lot about a circuit. If you look at this example, we have the current here. Okay, A1 is going to be measuring the current through R1, okay? Now, because that's the current coming out of the battery, that current is going to split off through these two paths and then come back together. So we know that is also going to be the current flowing through R5, okay? Through this one. Now, A2 measures the current flowing through R2. But what about R3 and 4? Now, for this one, we need to understand something about current. It's conserved in a circuit. So if you have this current going in this way, and you know how much goes that way, the rest of it goes in the other direction. So to get the current through R3, okay, it's equal to the current going through R4, because again, they are wired in series with each other. And that is going to equal the current flowing through R1, which again we measured using A1, minus the current going through R2, which again we measured using A2, because the current that doesn't go through that path must go through the other path. Okay, cool? Okay, cool. So, another important component of circuits is understanding how a switch affects it, okay? So if you got a switch, right, it can either be open, okay? If it is open, there is no current flowing, okay? Because it can't get through, okay? Where a closed switch means it's closed, you have a complete circuit, and current can flow, okay? There's a really good game called Crack the Circuit that can help you kind of figure out and make logical sense of how switches affect things in a circuit and also how things are connected. So if we look at this circuit, for example, if I turn on that switch, it turns on that light bulb. So we know that that light bulb is connected in series with a switch, where this one controls these two. Okay, and notice if I have them both together, this one is actually going to be brighter than the other two. Okay, so I want to get these all hooked up in series, complete my circuit. Okay, and there we go. The reason that the one on the left is brighter is because there's only one there. So it's going to get all of the voltage, okay, all of that energy from a circuit, where the two on the right have to share that voltage. They have to share the energy. So they're going to be a little bit less bright. I highly encourage you to check it out. Again, that's at crackthecircuit.com. So, batteries, we know what batteries are. We use them all the time. Okay, they provide a potential difference in the circuit. The two terminals of a battery are at different potentials, so they cause the electrons that are already present to flow from the negative terminal to the positive terminal, okay? AKA, they cause current to flow in the circuit. They push the current around the circuit. And that's why they have the kind of misnomer of electromotive force. Because we obviously need another word for voltage. We got voltage, potential difference, electromotive force. All meaning very, very similar concepts, okay? The basics though, the more potential difference you have, the more force, electromotive force you have, okay? And the more current that will flow in your circuit. Now, all of our circuits are also going to have some resistance. So when we talk about resistance in general, we're talking about a property of a circuit to resist the flow of current. If you have a current with low resistance, it doesn't resist the flow of current that much, and current flows more freely than in, say, a circuit with high resistance. The units for resistance are the ohms. So join the resistance, ohm. Okay, it's a peaceful resistance, full of monks. Okay, they're going om. You join them. Yeah, get it. Okay. Anyways, moving on. So resistance depends on a couple of different things. If you have a given, we're just gonna visualize this as kind of a piece of a wire. Okay. If you have a longer wire, you're gonna have more resistance. Okay, because there's more of it to get through. So resistance is directly proportional to the length of something. And it also has to do with the area. If you have like a little skinny wire, okay, all of the electrons have to go through there. Where if you have a bigger wire, okay, there's more area. So there's more room for the electrons to flow through. So they're going to flow a lot more easily. So resistance is inversely proportional to the area. And now it also depends on something called resistivity, okay? Resistivity, which we use the variable rho for, it looks like an italicized P, is an intrinsic property of different materials. Conductors, like copper that we use for wire, have super low resistivity, while insulators have high resistivity. Okay? There's a really cool mini lab you can do where you find the resistivity of Play-Doh. I highly recommend it. And we already did it in class if you are in my AP Physics 2 class. So let's talk about resistors. So whenever we need to control the current in our circuit, whether it's the circuit that powers our car or in our home or in a remote control, we're going to use resistors, okay? Now, we tend to think of resistors as in terms of Ohm's law, V equals IR, rearranged for resistance. It's the potential difference divided by the current. Okay, and this is what kind of provides the power to a circuit. So as current flows through a resistor, that electrical energy is converted into heat, okay, sometimes. Or if it's the resistor is a light bulb, it's converted into light energy. If the resistor is a motor, it's converted into mechanical energy, okay? But the rate at which a resistor, wherever it is, converts that electrical energy to whatever it is called the power of a circuit. So the power of a circuit, it depends on the current flowing through it and how much energy that current has, or the potential difference. Okay, so on your AP Physics 2 equation sheet, it is written as power equals current times the change in voltage. Now, often you'll see this in a couple different ways, because remember, we have Ohm's law, so we can represent current or voltage in a number of different ways. You could also rewrite this equation by subbing in delta V. It'd be I squared times IR, I times IR, so I squared times R. Or if you didn't have the current, you might plug in I equals delta V over R, and then you have delta V times delta V over R, or the voltage squared over the resistance. And all three of these equations can be used to solve for power. This is just the one that's on your equation sheet. Okay. Now, resistors, we typically think of as having the same resistance. If it's a 100 ohm resistor, it's a 100 ohm resistor. However, that's not necessarily always the case. Okay. Some resistors are what we call ohmic. Okay, they obey Ohm's law all the time and keep a constant resistance regardless of the current or voltage flowing through it. By following Ohm's law, we basically mean if you have the voltage and the current, okay, it is going to be a straight line with a constant slope equal to the voltage over the current, aka the resistance, okay? The slope of that line is going to be the resistance. However, not everything really follows that, okay? Here's some data collected in a resistance mini lab. Pull it up for you guys. For a battery and a light, or for a resistor and a light bulb. So if you look at the data, the graph right there, it is a nice linear graph. It has a constant slope equal to 29.5 ohms, which is good because it was a 30 ohm resistor. So pretty right on there. And that slope of it is the voltage divided by the current. That is the resistance. And you'll notice that it is constant. Where for a light bulb is a classic example of a non-ohmic resistor. You'll notice that these lower currents, it actually provides less voltage. It has a less steep slope, so it has a lower resistance. Where at higher voltages, okay, the slope changes a little bit and it has a higher resistance. So its resistance changes as the current and voltage changes. And that's what characterizes it as a non-ohmic resistor. Okay, cool? Okay, cool. So let's look at this just in terms of data, okay? Go ahead and take a second to look at those two data sets and determine whether resistor 1 and resistor 2 are ohmic or non-ohmic. Pause the video to check it out. Okay, so first let's look at resistor 1, okay? There's two ways you could do this. You could pretend and like have a little column here where you're actually solving for the resistance using voltage divided by current. If you did that, you would have, okay, 0.01 here, or 1 over 100. Here you would have 0.011, okay? 0.011, 0.0, gonna guess it's 0.12. Okay, and you will see that it is not a constant value, okay? It's not constant. If you were to graph the current versus current versus voltage for this one, it would not be a straight line. But resistor 2, okay, you'll see it's 1 over 50, 2 over 100, so 1 over 50, 3 over 150, which is 1 over 50, 4 over 200, 1 over 50, 5 over 250, 1 over 50. The resistance is constant. If you graphed it, it would be a very linear relationship, meaning that resistor 2 is ohmic, while resistor 1 is non-ohmic. Okay, cool? Okay, cool. Let's apply those power equations real quick in a little example problem. A resistor has a current of 12.5 amps going through it when connected across a 120 volt EMF source. Okay, calculate its resistance and power loss. So we have the current, which is 12.5. We have the voltage, which is 120 volts. Okay, so we can calculate the resistance by our voltage over current. When you plug that into your calculator, you get 9.6 ohms. You could also solve for the power using that it's the change in voltage times the current. You plug that into your calculator and you get 1.5 times 10 to the third. What is the unit for power? What is the unit for power? Watts. Okay, which we would probably write as 1.5 kilowatts. Okay, make sure you add that in. I'd forgotten to add that. Okay, the units of power is the watt. Watt is the unit for power. Okay, cool. Okay, cool. Okay, now, most of the time in most problems, we assume that whatever the voltage posted on our power source is, that is the voltage. However, most batteries are not perfect, okay? They have their EMF source, they have that different in potential, but they also have some internal resistance, okay? So that means that the battery actually uses up some of the energy, it uses up some of the voltage before the current even exits the battery, okay? Now, when we talk about this in detail, we refer to that voltage of that ideal battery is our EMF, E, okay? And if you were to go across this battery and measure its voltage, you would actually be measuring the terminal voltage, okay? So, the terminal voltage equals that EMF of the battery minus some internal resistance and the voltage that gets used up by that internal resistance, okay? In this situation, I'm going to represent that voltage, or we'll just do voltage lost for now, okay? Voltage lost in battery, okay? So we can actually use this information and solve for the internal resistance of a battery. I'm going to talk about it a little bit, but if you head over to YouTube and check out A-level physics, okay, they have a really good video about measuring the internal resistance of a battery, okay? So I highly recommend you check that out. But basically, based off this equation, we can't measure this directly, okay? There is no way to get inside the battery and measure this directly. However, okay, we can measure this, and this voltage lost in the battery we can calculate, okay, as our current that is flowing in this circuit times that small little resistance of the battery, that internal resistance, okay? So if you set up a circuit, okay, I'm going to go ahead and draw your circuit diagram. Okay, there is our EMF source, and imagine it connected to a little resistor R. Okay, and that whole thing is our battery. We'll measure the current in our circuit, and we'll have some load here, R, okay, which we will then measure the voltage across, okay, which will be our terminal voltage. So when we can calculate in all of that data, okay, we can get our terminal voltage, our EMF minus the current, the voltage lost in the battery. We can actually use Ohm's law to solve that. It'll be the current in our circuit times our little load R. Okay, now this I can measure, okay, and this I can measure using my ammeter. And that will measure using my voltmeter, okay? And in most of our labs, we just assume that's whatever is applying to the battery. However, if you actually solve this out, you're not gonna get a perfectly neat constant voltage, okay? I did this for my internal power supply, and I ended up with this equation, okay? So I have my potential difference versus my current. In order to make sense of what this means, let's go ahead and go back and see how we can reorganize that equation to make it make sense. Okay, so with a little bit of rearranging, I'm just going to rewrite it as our terminal voltage, which again we're measuring using our voltmeter, equals minus IR plus E. Okay, and that is the slope of a line, okay? There's our Y, that is what we measured, equals MX plus B, okay? Oh, technically it's this way, okay? So current is RX, okay? You'll see the current is on the Y-axis, so that is my X, okay? This is the voltage coming out of the source. It is our EMF. Okay, if you kind of extrapolated this line to where you have no current, you can't actually have no current, so it's not something you can measure. But that would be the EMF of our battery, where this number right here is that internal resistance. Okay, so the internal resistance of my variable power supply that I did this data on is 0.2661 ohms. Okay, cool. Okay, cool. And again, if you're kind of confused on this internal resistance stuff, I highly recommend you check out those A-level physics videos. Okay. In a problem, it might look something like this. A battery has an EMF of 24.0 volts. When it's connected to a circuit, it delivers 3.4 amps of current, and we know the battery has an internal resistance of 1.5 ohms. So it's asking you for the terminal voltage, the voltage that you would measure across the terminals of the battery. Well, our terminal voltage, that's not how you spell terminal voltage, is going to be equal to our theoretical voltage. So hopefully we get 24.0 volts. But we know that's not true because some of the energy is going to be eaten up by the battery. So we can use V equals IR. So it would be 24 volts minus the voltage from the battery, which is that 3.4 amps times that 1.5 ohms. Okay, because of this idea, at higher currents, that internal resistance is going to have a lot more of an impact. Okay, at lower currents, it doesn't have as much of an impact. That change is going to be pretty small. But as this number, sorry about that. But as this number increases, all of a sudden the internal resistance of the battery starts making a difference in your measurements. So the terminal voltage here is 24.0 minus the voltage lost in the battery, 3.4 times 1.5, which gives us a value of 18.9 volts. Okay, so that is the voltage that's actually available for our circuit. There's an external, so if there was an external resistor in the circuit, it's not going to get that, in theory, voltage. It's going to get that 18.9 potential difference that's coming out of the terminals. So how much power is it going to have? Okay, how much power is it going to lose? Well, it's not going to get the 24 volts. It's going to get the 18.9 volts times the current in that circuit, which was 3.4 amps. Okay, and when you plug that into your calculator, you get 64 watts. Okay, cool. Okay, cool. Now, some of our circuits are going to have both resistors and capacitors. If you have resistors and capacitors in a circuit, we call it an RC circuit. Okay, I'm going to go ahead and take a pause and plug in my computer so it doesn't die while I'm doing this. And of course, this is going to do it. Hold on, we're going to pause. Okay, so circuits that have both resistors and capacitors are called RC circuits. We'll be getting into those more later, but the basics is that you're only going to be asked about RC circuits in one of two different states. So if you first connect a capacitor to a circuit, okay, no charge is built up across the plates. So it's still going to have the potential difference, and the capacitor is just going to act like a wire. Okay? The current is still going to flow until the charge has built up on the plates, and we call that steady state. So once the capacitor is in steady state, it's built up its maximum amount of charge. In that case, no more charge can flow through, okay? There's no more electrons or force that's going to be pushing in those particles, okay? So once it's full, no charge can flow. It acts like an open switch, okay? Therefore, there's no more current going to be flowing in the circuit. And when it's in that state, you can look at the potential difference across it, and it's still going to be equal to any other things that are connected against it in series. Now, Kirchoff was a really smart dude, okay? He kind of put into law some of the things that we already knew about circuits. The basics of his two rules are that the positive currents entering a junction, like this one right here, must equal the currents leaving the junction. Makes sense? Okay. Also, his loop rule says that the sum of the potential drops across a closed loop is 0. So while a battery adds voltage, each of the resistors drop some of that voltage. Okay. In this circuit, for example, there's two loops. There is this loop, okay, and there is this loop. So you can use this to actually trace the voltage in a circuit. If you have a voltage from the battery here, this resistor is going to eat up some of it, and this resistor is going to eat up some of it. And when you add those two up, they must add up to the battery voltage, meaning that the total voltage through that loop is 0. Okay, same for this loop. Okay, the voltage from the battery has to equal the voltage drop from R1 plus the voltage drop from R2 plus the voltage drop from R3. Okay, and that's how you can use that loop rule to kind of solve for anything in a circuit. Okay. This also helps us make sense of currents in a circuit. So if we were trying to rank these currents, let me go ahead and erase this so we have a clean place to start on. Okay. If we're going to solve for some of these currents, I1, I2, and I3, okay, well, first, we know that the most of the current is going to come out of the battery. So I1, okay, is going to be the greatest current. then that current is going to get split between I2 and I3, okay? If all the resistors are the same size, more current is going to flow through the path of least resistance, okay? Because this path only has one resistor, more current is going to choose to flow through that path than to flow through these two resistors, okay? Through the path on I2. Now, this also helps us make sense of these voltage drops. So we know voltage equals current times resistance. If all resistors are the same size, the one with the most current is going to have the most voltage, okay? Most current, most voltage. So we know that that's going to be the voltage through R1, okay? Because it's the one that has the highest current flowing through it. Now, the next one then is the one that has I3, so that'll be the voltage through R3, and I drew that too far over. Now, R2 and R3 have the same current flowing through them, and they have the same resistance, so they're going to get the same amount of voltage. Okay, so the V R2 is going to equal the voltage drop from R1. And we know that when you add all of these voltage drops to get, nope, sorry, that's a lie. Yep. When you add the voltage drops together for a closed loop, it'll get the battery voltage. Okay, and that's an overview of everything that goes into our circuits. Okay, cool? Okay, cool.